Okay, Samuel, so this chapter sets the stage. What's the overall plan?
Yeah, we're laying groundwork. Part two's plan is to build up to training our first model.
Cool. So we're diving into the specifics. What exactly are we doing in Chapter 10?
Chapter 10 will handle data, parsing and prepping it.
Parsing? Like finding the right bits of data?
Exactly. We'll create the routines to work with our data.
And that data will get used in Chapter 11, right?
Right, then we'll use that prep data to train our first model.
This seems crucial. But what about the context?
Crucial for understanding any project. We'll look at how our data is formatted and where it comes from.
Data sources, gotcha.
Plus, we'll pinpoint limitations of our project.
Like any roadblocks?
Precisely.
That's a fantastic overview. Why is this crucial for deep learning?
Without it, your model's like a car without a roadmap. You might have a fancy engine, but you won't know where to go or what to expect.
So, Samuel, we're diving into a pretty specific use case. Detecting lung tumors from CT scans. Why this particular problem?
Well, Alfred, it's a real-world challenge. Early detection is crucial.
Right, but a huge haystack of data.
Exactly. Tons of scans, and finding the needles, malignant tumors, is really tough for humans.
So, deep learning's the answer?
It can automate the process, potentially. It's a tough problem.
So, you're saying this isn't like a solved problem?
No, not really. While a lot of research has been done, it's not trivial.
Why is this good for learning PyTorch?
Because you'll be tackling a cutting-edge, unsolved problem with a powerful tool.
Why not something simpler?
This problem is complex enough to be challenging, but not so complex it's impossible. It pushes your skills. Lots of good research and open-source projects are already there for you to learn from.
The goal isn't perfect clinical accuracy, though.
Exactly. We're using it for learning PyTorch techniques, not developing a diagnostic tool.
So, we're learning about the journey, not just the destination?
Precisely. Pre-processing the data, setting up training, even evaluating performance are all essential. You can apply these skills to many other projects.
Can you give an example of pre-processing like for this problem?
Sure. For example, preparing the CT scans, ensuring they're consistently formatted, or adjusting brightness or contrast to improve quality.
Sounds complicated.
It is, but essential. You'll find common issues.
This is a pretty good teaching tool then. So, you're saying that even though we aren't going for perfect accuracy.
Exactly. We want to equip you to handle real-world challenges, even if they aren't perfect.
That's a great point. Okay, Samuel, this project sounds ambitious. Building a model for analyzing CT scans, huh?
Yeah, it's a complex task. Part 1 laid the groundwork, but Part 2's different.
Crucially different. You mentioned a lot of data manipulation. Is that right?
Exactly. We're not starting with a pre-packaged dataset. We have to prep the data ourselves.
So, no readily available libraries for this type of medical imaging?
Nope. That's a big shift. We'll spend much more time understanding our data, cleaning it, and making it ready for the model.
That's going to be quite a bit of work. How long do you anticipate this data prep stage lasting?
Well, it depends on how the data looks, but it could easily eat up more time than the model building itself. Expect weeks.
Weeks?
Potentially. We also need to account for confounding factors. Imagine trying to find the tumor in a scan filled with noise.
You mean like distractions in the data?
Limited data, computational power. It's a real-world challenge. It's not just about building a perfect model, it's about designing a viable approach.
Right. And GPU access is essential?
Absolutely. Training on a CPU could take forever. A good 8 gigabytes of RAM, ideally.
So, we're not just looking for a fast solution, but a viable one?
Exactly. This is how things work in the real world. We're not always going to have infinite resources.
And the chunk-based approach?
Breaking it down like an assembly line. Each step processes the data and passes it on. A more manageable way.
A very good point, Samuel. So, we're moving away from a simple input-output model for medical imaging.
Right, we need to understand the underlying medical domain, like radiation oncology.
Why is that so important?
Deep learning isn't magic. Applying it blindly won't work. We need the medical insight to understand the problem and design better models.
That's a crucial point. So, learning the domain before the code is a very important insight?
Absolutely. Combining medical knowledge and deep learning intuition is key. We need to blend the two for good results.
So, Samuel, you're saying a CT scan is basically a 3D X-ray?
Yeah, that's the gist of it. It's like taking a bunch of X-ray slices and putting them together.
But how does it create a 3D image?
Instead of just a flat projection, a CT scanner uses X-rays from many angles. It measures the amount of radiation absorbed by the different tissues.
So, it's not just about what's there, but how much.
Exactly. The more dense the material, the more radiation absorbed. That translates into different shades in the image. Bones show up white, air black, and so on.
Okay, I get the density part. But what about this voxel thing?
A voxel is like a tiny 3D box. It represents a tiny volume of space within the scan. Each voxel has a number value corresponding to the average density.
So, it's like a 3D grid of these density readings?
Precisely. And these voxels are arranged in a grid. The key difference from a 2D X-ray is that a CT scan keeps the third dimension. It's not just a flat projection, right?
Right. So, you can actually see inside things?
You bet. You can even hide certain tissues from view. Imagine just seeing the bones and the lungs, for example.
That sounds pretty powerful. Why are CT scans harder to get than X-rays?
They require specialized equipment. CT scanners are often expensive and need trained operators. Plus, there are patient privacy regulations to consider.
So, the data itself is a digital format?
Yep. It's all digital numbers, no film involved. The output isn't immediately human-readable.
Interesting. What do you mean by that?
The raw data needs a computer to process it and turn it into something understandable for us to see. The settings used during the scan also influence the final output.
And that's why you mentioned voxel shapes might not always be perfect cubes?
Exactly. The way the scanner measures distances across the patient is not always uniform along all the axes. The patient moves along one axis. That's why we get these rectangular prism voxels instead of perfect cubes.
Wow, a lot to think about. So, understanding these details is crucial to using this data effectively, right?
Absolutely. You need to understand your data to make good choices on how to use it. It's important for your own projects too.
So, Samuel, this lung cancer detector project, it's ambitious. 5 steps. How do we tackle something this complex?
Yeah, it's a multi-layered problem. We gotta break it down into smaller, manageable pieces. First, the raw data. Think of it like, well, unpacking a giant box of CT scans.
Unpacking a box of CT scans? Interesting. What exactly do we do with them?
We need to load that 3D data, get it into a format PyTorch understands. That's step 1. Pretty standard prep, really.
Okay. Step 2 is segmentation. That's where we identify potential tumor spots. How's that work exactly?
We're essentially building a heat map. PyTorch helps us pinpoint the voxels, the tiny 3D blocks of data, that might be part of a tumor.
So, we're zeroing in on specific areas? That sounds helpful. What about step 3? Grouping those voxels into potential nodules?
That's finding the clusters of those hot spots. We're not using PyTorch directly for that. It's a separate prep step. Think assembly lines. We're finding the centers of those groups.
So, we're turning scattered data points into organized clumps?
Precisely. And then we've got step 4, nodule classification. We use 3D convolutions, kinda like a zoom lens, to analyze the nodules.
3D convolutions like in 2D? More powerful?
More powerful, yes. More layers mean we can consider a wider scope of features, helping us distinguish tumors from healthy tissue.
Makes sense. So, it's like building a classifier specifically for nodules. And finally, diagnosis.
Correct. We take all those individual classifications and decide if the patient has cancer. A simple maximum approach works well here.
So, we're looking for a yes or no answer.
Exactly. It's a binary classification. But importantly, we're focusing on getting these modular components working well first. We're kind of building the pieces and fitting them together.
That approach makes sense, especially with how important it is to have specialists confirm suspicious cases.
Well, working from the middle helps us focus. Imagine if we had a team of people. Each could concentrate on one task, a clear-cut role, making the entire project way more manageable. And then clinical users often want the tool to highlight suspicious cases for review. Adapting to that kind of use would be easier if we build in layers.
Intriguing, that approach, Samuel. It makes it clear we're not just building a program. We're building a workflow.
Exactly. And we're taking inspiration from experts. Other research has done similar work, and we want to learn from their successes and mistakes.
So, we're leveraging prior knowledge, like seasoned researchers.
Yes, we're standing on the shoulders of giants, Alfred. It's smart to learn from the best.
That's a great perspective. I'm looking forward to hearing how this approach impacts the outcome. We should also look out for cases where it might not work and what modifications might be needed then. So, Samuel, you mentioned throwing data at a neural network. Is that really a viable strategy?
Well, in theory, sure. But practically, it's often not the best approach.
Why not? Seems like a brute force method.
It's like trying to find a tiny needle in a massive haystack. You could throw hay at it, but you'd be spending a ton of time and resources. And you might never find that needle.
But lots of deep learning is successful. Couldn't you just throw enough data?
You can, but it depends on the problem. Medical imaging is different from recognizing cats in pictures. Medical data is often scarce for rare conditions. Plus, a lot of the data is essentially noise. 99-point-something% of a scan might not be relevant.
That makes sense. So, there's a better way?
Absolutely. The method in the text breaks it into smaller, manageable steps.
That's interesting. Can you explain how that works?
We focus on tasks like identifying potential tumors first, then classifying them. This allows for more precise analysis and targeted training data. Imagine focusing on the needle, not the entire haystack.
How does that improve learning?
By isolating specific tasks, we can tailor the models. It's like having a specialized tool for each job.
So, training on just the tumor part is better?
Precisely. It's easier to find the signal tumor when you're not dealing with too much noise, rest of the image.
So, the end-to-end approach, throwing the whole image at the network, is not always the best for this type of problem?
It can work, but it might not be the most efficient or the best approach for learning and understanding. It's like trying to teach a general-purpose tool to perform many complex tasks instead of specializing tools for individual tasks.
What about those pre-trained models, like fast RCNN or mask RCNN? Why aren't they ideal here?
They're great for general vision tasks, but those models are trained on huge datasets, and datasets aren't usually constrained by rare classes. The amounts of data needed to properly train would be prohibitively expensive. Imagine trying to train a model to identify the rare needle from the vast amounts of hay.
So, this approach is less about brute forcing the problem and more about thoughtful design?
Exactly. It's about understanding the problem and creating targeted solutions. The structure and targeted approach allow for higher quality results and are better for learning how to solve the problem.
Okay, so it's about creating models to be less noisy?
Yes, the models are designed to focus and isolate relevant data.
So, Samuel, you're saying a nodule is basically any lump in the lung?
Yeah, pretty much. It's a general term, you know? Think of it like a blanket term for any little bump or lump.
But there's a size cutoff, right? 3 centimeters or less.
Exactly. Anything bigger than that's considered a lung mass. But for our purposes, we're lumping them together. It's a bit arbitrary, and makes it easier to program, since we're using the same code paths.
Makes sense. Why that arbitrary cutoff? Is it just about computational efficiency?
Well, yes, but also, most important is finding the cancer. We're looking specifically at nodules to find cancer that will present as a nodule. It's easier for the AI to focus on that shape than trying to search all sorts of tissues in a CT scan.
Interesting. So, this is really a way to simplify the data for the AI, right?
Exactly. By restricting the search area to nodules, The AI can learn to distinguish between different types of nodules, and importantly, between cancerous and non-cancerous nodules. This is way better than looking at everything and trying to figure out what's what.
Okay, so you're saying the nodules we're looking for are a small mass, potentially cancerous, right? And what else could a nodule be?
Right, a nodule could be a number of things, infection, inflammation, blood flow problems, even just a malformed vessel. Not all nodules are cancerous.
So, we're hunting for the needle in the haystack, but we're only looking in the haystacks that could potentially have a needle.
Precisely. We're making the search space much more manageable for the AI, allowing it to concentrate on what's important.
It seems like this targeted approach has huge benefits in terms of speed and accuracy.
Yes. And as we've learned in this part of the chapter, it's about knowing the field you're in, like radiation oncology. Deep learning is powerful, but you need to give it context.
Right? The nodules are like little puzzle pieces that the AI should be able to figure out now.
Exactly. The smallest nodules are tiny in the millimeter range, but still they might be 1,000,000 times smaller than the whole scan, which is pretty amazing, actually. And a lot of the nodules aren't even cancer. It's reassuring.
So, Samuel, this Luna Grand Challenge dataset sounds pretty cool. It's open source, right?
Yeah, totally open. Researchers can access it, use it, and even improve detection methods. It's like a massive public competition for better lung nodule detection.
And these CT scans, they can be pretty tricky to work with, right?
Absolutely. Different scanners, different settings. Sometimes, parts of the scan are marked as outside the field of view. It's important to realize that real-world data isn't always perfect, even though this Luna dataset is generally clean.
So, there are ways that the data can be misleading or even harmful, even though the data is clean?
Precisely. You have to be aware of potential issues. One thing that could go wrong? Certain areas might be flagged as outside the field of view but are, in fact, inside it. The different settings, well, you could potentially get false positives or false negatives.
What about these two tracks, nodule detection and false positive reduction?
Nodule detection is like the segmentation task, finding and outlining the nodules. False positive reduction is more like the classification task. It's identifying which areas are definitely nodules and separating them from areas that look like nodules.
Got it. So if I want to start building a detection model from scratch, where would I start? The lung nodules themselves aren't the only thing to look for?
Yeah, the scans can be very complex. The scanners have inconsistencies. The location of these suspicious areas is like, we can't just assume the nodules are in a perfect spot.
This is super important. So, Luna 2016, you said? Is that a historical dataset?
Exactly. It's from 2016, so it's historical data. But it's valuable because the teams that worked on it developed really sound detection and classification methods that we can learn from. Their results provide a good benchmark, and the criteria are very well standardized.
So, a team can compare their methods to established standards and, hopefully, improve on them?
Exactly. And they have to publish their methods and results to be part of the leaderboard, which forces rigor and comparability. It's a great way to encourage further research in medical image analysis.
That's fascinating. This dataset is a treasure trove. Thanks for that breakdown. All right, Samuel, so we're diving into the Luna data. Sounds like a hefty download. What's the deal with this dataset?
Yeah, it's pretty substantial. Around 120 gigabytes unzipped, plus cache. That's a lot of CT scans. Crucial for this project.
So, where do we find it? And how big a download is this?
It's on Zenodo, or academic torrents.
So, there's a crucial step before training. Downloading the data. How much space do we need?
Well, the main data is around 60 gigabytes compressed, which expands to 120 gigabytes. You also need about 100 gigabytes cache to process it efficiently. Total, it's quite a bit of space.
Okay, so we got the Zenodo or academic torrents download. But what about these subsets? Why are they needed?
These are like smaller, manageable parts of the whole dataset. You can use just one or two subsets if needed, saving space.
So you can just use a fraction of the data if you're short on space. Clever. Is there any downside to using a smaller subset?
Absolutely. Training on less data usually gives a less accurate model. But if you're crunched for space, it's a good option.
Right. And we're looking at 10 subsets in total?
Yes. You need to extract them individually into those subdirectories. They're like individual cases.
And what about these extra CSV files? Candidates.csv and annotations.csv?
Those files contain crucial information about the images. Things like what's in each CT scan. Very important.
So, they're metadata? Metadata about the data itself. So, we need to download these CSV files too. Are they essential?
Yes. They're essential for training. They help the model understand the specific aspects of the images.
Okay, so we need to download the data. Then, extract these parts. Then get the candidates and annotations CSV files. Is this the complete process to get ready for the training part of the project?
Yeah, that's pretty much it. Once you've got at least one subset and the CSV files, you're good to go.
Sounds manageable. What about troubleshooting? What if the download fails?
Check your internet connection. Double-check the domain name. It's lunal6.grand-challenge.org. Make sure you've got the right version of the extractor for 7Z.
So, Samuel, we've laid the groundwork. Impressive groundwork.
Thanks. It's important. You know, just figuring out the context is huge.
Exactly. But it feels abstract. We haven't written any code yet. Is that concerning?
Absolutely not. Think of it like building a house. Foundation's critical.
Right. But how does planning the project structure help with the coding?
Well, we've defined the project scope. You know the what and how.
So, we're not just coding randomly?
Exactly. We have a direction now. Everything flows logically.
Okay, but still, no code means no progress?
Progress, you know, isn't just about lines of code. It's about understanding. We've understood the project's context.
Makes sense. This deep understanding, that's something powerful.
We've also sketched out a blueprint for future steps. Critical stuff.
So, you're saying we should value the planning, even without tangible results?
Absolutely. The design work is the core of what we do. It's the basis for solid solutions.
I see. So, this groundwork is going to pay off in the implementation phase?
Big time. It's not just about the coding. It's the thinking.
And that's crucial. Good point.
Chapter 10's data loading will be smoother because we've already established the framework.
So, skipping exercises for this chapter is intentional?
Yes. We're focusing on information, not exercises this time.
Okay, makes sense. Good to know.